Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the second of, I think, at least 5 talks today. So if someone attends all 5, you get some sort of medal, I think. Please help me welcome Ann Mulhern, who's a graduate student at the University of Wisconsin in Madison, who's working with, technically advised by Charles Fisher, but also working with Ben Lidlett, and she's going to tell us what she's up to.
Okay, thank you. I'll just go and proceed then and begin my talk. So my whole point is that the size of proofs is just getting larger. This is one example. There are quite a few other notable ones and more that were brought up in the workshops that I attended yesterday. And this statistic is taken from the proof of the C compiler backend. The way the C compiler backend was written is that first the definitions of the compiler were written as a set of functions in Coq, and then the proof that the compiler was actually semantics preserving was developed around those definitions. So in this case, the definition of the compiler consisted of about 13% of those 35,000 lines of code. Everything else went into proving that the semantics was preserved. And I work in particular with Coq, which generates concrete proof objects. And the problem here is proof objects can be orders of magnitude larger than the proof scripts that generate them. And there are ways to drive this ratio down. Modularization helps to drive it down, but very powerful tactics and intelligent use of hints will in fact tend to drive this ratio back up again. And of course, we're all aware that programs can be larger still. In 1991, the first release of Linux was 10,000 lines. 15 years later, it's up to 7 million lines. But people do deal with that. And one of the ways they've dealt with it is to develop IDEs, tools for visualizing and understanding the large volumes of code that they have to deal with. And so the idea is we want to advance the notion of an integrated proof environment, something that integrates a lot of tools to help us deal with proofs. But it's like the unicorn of medieval mythology. We think we know sort of what it should be like, but we don't get a chance to actually interact with it. Okay, so all I'm doing here is advancing a point of view that I want to convince other people of. First is that tools and techniques that are already available in IDEs can be transferred to IPs. And second, that they ought to be. And I'm going to dwell really hard on the second point and give the first point fairly short shrift. Okay. First, what I'm going to do is I'm going to explain who I am, what I'm trying to do, why I feel that what I'm trying to persuade you of is true. Then I'll talk about some tools and techniques that I've identified. And then finally, I'll talk about the mechanisms to put these tools and techniques in the IPE. So what do I care about? I care about formal proofs of programming language properties. And something that gathers together those ideas is the work on the Popplemark challenge. I'm also interested in the generation of certified programs. I'm interested in the generation of them by extraction. A number of proof assistants provide an extraction mechanism. You can take the proofs in the proof assistant and extract them to an actual language that people use. But I'm also interested in the opposite, where one might take a program written in an existing language, pull it into a proof assistant, and then do the proving.
What do you mean by insertion?
I'm saying that is the opposite of extraction. There are actual formal mechanisms to take proofs and dump them out as correct programs. But people have also worked toward the other way, where they take a program, they translate it into the language of a theorem prover, and then they'll endeavor to prove stuff through that theorem prover. So that's insertion, the opposite of extraction. So that my argument is that programming language proofs are different. We need them to be easy to modify and reuse. So this is different from a lot of mathematical proofs, to which some theorem prover tools are directed. When we have developed a proof of the four-color theorem, we can rest on our laurels. It's more or less done, right? But if we develop a proof that a compiler is correct, or we develop a language that is type sound, that's only good so long as the compiler and the language stay as they are. As soon as we augment them, or our compiler gets more ambitious, tries to compile more of the language, we need to redo the proof. Another problem is that proofs frequently proceed by induction on multiple cases, and automating that sort of thing is turning out to be particularly challenging. And finally, though, there's a sort of a positive thing about programming language proofs. Often, when we're dealing with mathematical proofs, half the struggle is we set up the problem, but then some of the struggle is really to figure out how to prove it at all. So you'll find that in the mathematics world, people will come up with a newer, much better proof of some interesting result, and that in itself is important. But with the programming languages sorts of things, we know the overall approach that we have to take. That is really not the problem. The problem is that what we're trying to prove has a certain inherent complexity. We all know the four-color theorem. You can take a map, and it requires a maximum of 4 colors to prove it, and that can be stated fairly simply. But if I want to say I need to prove this language is type sound, I have to state all of its type schemas and all of its evaluation rules, and that's immediately part of the problem. But at least I do know how to tackle that problem. So there's this wonderful theoretical result called the Curry-Howard isomorphism, which identifies proofs and programs. And that's very pleasing, but what I'm trying to say is that we have to deal with proofs as well. We have to extend, refactor, and debug them. And so what essentially we've done is we've taken all the sort of grimy and difficult aspects of dealing with programs and dragged them into the formerly happy and clean proof world. But the idea is we can tackle these similar problems with similar techniques. And so these are a lot of proof assistants. They were identified in this paper, The 17 Provers of the World. And they're all quite significantly different in important ways. And if you're counting, just to make sure, there was one missing. Coke is my favorite, and it's the one which I must take all examples from because it's the one with which I have true familiarity and experience. But I feel that some of what I'm saying here can surely be extended to others. It just requires people who have that sort of experience. Okay, so what are the tools and techniques? The first are really what I've identified as common conveniences, things without which an IDE would not be releasable, really. And there are a couple, I've divided those actually into two sorts. There are ones where you can sort of multiple views, looking at and manipulating, looking at the text to see various things about it. And another aspect of these things is automatic refactoring, which has actually gained ground probably in the last 5 years. Refactoring is what we do when we change the code but preserve its behavior. And when we automate that, we simply let our little refactoring tool do that for us. And of course, we would make these changes to make our program clearer, more modular, faster, so forth. And so what I have here is just an outline view of the list library, which comes along with the Coq distribution. And the idea here, the list library itself is 600, 700 lines. It's hard for a person who maybe wants to use it to immediately grasp what it has to offer. The outlining view just lets us get a look at things. Sections are Coq's mechanism for organization. The hints are things that it adds to a database so that we can use Coq's various automatic mechanisms to try to prove our goals automatically. And I visualize those as hammers waiting to hit a nail that comes along. And of course, we can expand this a bit and look deeper and see that the functions on lists are mapped fold left and fold right, which we would expect if we're familiar with Objective-Camel. And we could use this also to navigate and look at our source code. So if we were particularly interested in the map section, we could click on it, and that would lead us to the proper position in the source code. And what we look at, we can see that all of these lemmas are collapsed. In Coq, every lemma that you have here would have an associated proof after it. That is the paradigm that they use. But we consider that I, as a user of list, am interested in using these lemmas, and I don't really, at this point, care how the proofs have been developed. So we can collapse them, but if we wanted to, we can click on the expansion triangle here and expand this thusly and see what the proof amounts to. And also there's this notion of refactorings, and this is just a possible list of what sort of refactorings might be useful in Coq based on my own experience. I'll just focus on one of them. There's this notion of making a variable implicit. So the idea is in Coq you can define things, and some of the variables in your definition it may be possible to make them implicit because their value can be inferred from the type of other variables, because Coq has a very rich type system. But the point here is if a variable is explicit, you must give it a value. If a variable is implicit, you may not give it a value. If during the course of your developing a proof, you decide that in fact you want this variable to be implicit, you must change not only the definition, but all places where the definition is used. And you can either do it by hand through multiple files and so forth, or you can allow a little refactoring tool to do it for you. And this is not a whole lot different than discovering that you have a procedure, and the procedure takes as a formal parameter something which is no longer used in the body. You wish to eliminate it, to tidy up, and you can use a refactoring tool to do that.
So how is that an example of that you get its value from the types of other things?
Yeah, I could show you an example of this, but Coq has a very rich type system, and the type system includes, you can allow, the types are actually lemmas. So you may say I take a definition, I give it a nat, which a natural number, but I also give a proof that this particular natural number is greater than 0, say. So if I supply the proof that 6 is greater than 0 for an elementary example, then I know that the implicit variable must be 6. So I can drop that out. And the other thing that I want to say is that I feel that where refactoring is concerned, a partial solution is good enough. I gave this very similar talk at UITP, and one of the attendants there said that she had heard that some other people had devoted themselves to this refactoring problem. Finding out that it was too difficult, had chosen some other problem. And what I feel is what people are doing is they're setting the bar too high. They're saying, well, our refactoring is no good unless it handles everything, unless when we apply it, it gives us back a correct proof. But I'm saying it's okay if when we apply it, it does 9/10 for us and leaves 1/10 remaining. So the idea here is, in this example, we might be interested in defining things in levels. And this is a lot like delegation with an object-oriented language, where we delegate some actions to an object that our object holds internally. In the same way, we might prove some simpler facts and then use those simpler facts in a larger construction. So the idea is I've defined a map here in pseudocoq, so as not to take up too much space. And it does the simple things that we're familiar with a map. And down here I've defined a store, and the store has to have these additional properties, right? But essentially I've proved that in my map the lookup is correct, that if the key is in the domain, then my lookup will return the value, and if the key isn't, then lookup definitely won't. And all I really want to do here, when I define that lookup is correct for the store, is to use this lemma here. So I can essentially allow my refactoring tool to give me, to prove this wrapper lemma. I may have to wrap many lemmas. Some may in fact fail, that my tool can't prove them. But if I've wrapped most of them, then that's really eased my development. Okay, so another idea, and we're changing gears a lot. Oh, and by the way, I should mention that those ideas I've shown, they're very obvious, outlines and collapsing and expanding text. Those are just the beginning things that would be very useful and, in fact, quite straightforward. Obviously, in a full-fledged IDE, we have other more powerful things, looking at the call chains and so on, which are also interesting. But if we move on to software visualization and if we move on to proof visualization, this is actually, the ideas are really taken from a paper by Ball and Ike that came out in 1996. And their idea is that there are certain properties that a programmer is interested in, but these are merely unary properties. These can be encoded with color, and we can use this color to allow the programmer to see these properties over large projects and many files. So here's a shot from this paper. This is 49,000 lines of C code here. And the idea is that the color shows the nesting depth. So the very palest green at the bottom indicates a nesting depth of 4, which means that these lines of code are nested beneath 4 conditionals of some sort. At the very top, in pink, we find that these lines of code are nested beneath 13 levels of conditionals or more. And you might think that, well, perhaps this is a trouble spot. This code nested so deep is really very fragile and breakable. And we can use the same ideas for proof visualization. A lot of theorem provers have this automated portion where they use lemmas that they themselves choose. It would be interesting to know what lemmas are weighed on very heavily, are used constantly, and what lemmas are in fact very infrequently used by the automatic system. Revision information is interesting to both programmers and proof developers. Different styles allow different proportions of proof to definitions. And goal depth is really very similar to nesting depth. So in a lot of theorem provers, actually, one may start with a lemma that one is attempting to prove, and one may choose to divide it into multiple subcases to address the proof more easily, and that little dashed line going behind the curtain indicates that there may be more subgoals than just that 3. And one may continue this process of subdividing these goals and so forth until finally one gets to something one can actually prove. One proves it, and by having proved these 2 subgoals, one ends up proving the whole thing. And one can proceed with this process. We prove another subgoal, and then we've gotten all the way there. And so actually when I was at the User Interfaces for Theorem Provers workshop, somebody had developed a very nice swing-based way of looking at these sort of proof trees and so forth. And the problem is that sometimes this big, complicated tree is actually more than what we want to really look at. And so the insight here is we can encode this depth just using color. And so what we have here is actually a colored version of a proof of progress for references. And you can see that there are these big sectors where I had fallen to a depth of orange here, and some smaller sectors where I had even gone a depth greater. And the interesting thing to me was that while I was doing this coloring, I sort of actually began to wonder why certain things were at such a depth because they shouldn't have been. And I found out that in the case up here, I had quite automatically ended up dividing a goal into subgoals when that was completely unnecessary. And for a proof, a math proof, which is write once and is good for all time, that's no big deal. But in the case where you're actually may have to expand the proof at some subsequent time, and these 2 subgoals might turn into 17, then finding out that you don't need to break up the proof at all is actually a gain. So this got various of us at Wisconsin thinking about how lovely it would be. I've been in this situation, I'm sure other people have been in this situation of looking at generated assembly code. And we all know that that can be unpleasant, especially when we're confronting assembly code that has been generated by an aggressively optimizing compiler. And we find that we're staring at actual chunks of assembly code, and we know not what part of the source code they were generated from. And it would be really nice to have some sort of tool that allowed us to identify a particular line of assembly code and find a nice visual mapping back to the source code from which it was derived. And similarly, in my work, I'm interested in manipulating proof objects. And so what we have here is the tactics that prove the decidability of equality on lists. Here we have the generated proof object that those tactics caused to be built. And here we have the extracted program. And the idea is that we might highlight a tactic, say auto, and we would find that here in the proof object, the particular terms that were generated by that tactic are highlighted. In this case, we see 3. And we could also see that in the case where we have an extracted program, then the terms in the program that corresponded to the proof terms are also highlighted. And so there's no analog really of this in IDEs of the sort I've mentioned, but as I said, something where you could map source to assembly would be very nice. So, and the mechanisms, I argue that the mechanisms are actually more or less available. Things like those text views that I showed are very simple. You just have to look at the text and develop the appropriate GUI sort of develop the appropriate GUI. Things like the mapping between the tactics and the proof object are harder, but of course we have interacted with debuggers and we're familiar with the process of stepping through the assembly language, and as we do so, we see that the debugger maps us back to the source. And obviously this is because we've compiled with the debugging flag set, and so the compiler has dumped various additional information in tables and so forth into the generated object code, which the debugger cooperatively reads. And things like the refactoring, it really depends on how ambitious your refactoring is. Very simple refactoring could, in fact, work entirely on the text, but a more ambitious refactoring that actually manipulated the proofs, the proof objects themselves, might have to use a combination of these techniques. And the same with the proof visualization in the large. So what I'm saying here is that IPs don't really exist, but that there's beginning to be a greater and greater need for that technology. And that it's not all entirely thought out, because in the area of these refactorings and so forth, there could be considerable interesting technical challenges similar to the ones that people have faced and overcome in the software engineering world. Oops, and I went one too far, so that completes my talk.
Questions?
Yes?
Maybe I came in a few minutes late, so maybe you mentioned this already, but what do people do now? I mean, when they're using Coq, for instance?
Well, the focus, well, there's actually two levels. Either they use something that's, in Coq, either they use something that's similar to an ML top level. Coq also provides an IDE, and the IDE has certain actually nice features involving one can graphically grab a hypothesis for one's goal and say, okay, apply that. So it has some nice features, but the features are all directed toward very interactive theorem proving. So the features are not directed toward subsequent proof management, things like that. And that seems to be pretty much the trend for user interfaces. They come up with clever ways to help you develop your proofs rather than machinery to help you manage them, I think. Yes.
Oh. Sorry, what's the useful lifetime of one of these theorem provers? Like how many years?
Yeah, that's a great question, actually, and that also came up at UITP. So some theorem provers are real existent usable titans. Coq is actually doing quite well, and it's thriving. It's been around for a while, and I expect it'll be at least around for another 10 years. But on the other hand, there was a very interesting talk at UITP where there was this notion of using web interfaces for theorem provers. And the reason for that is there are a number of well-respected theorem provers which are in fact kind of staggering along on OBS that only run if you, one example was he found he had to downgrade his kernel in order to install this theorem prover. So there's kind of a spectrum of things like, I think, New Perl and Coq, which are really solid, and I can slap it on my laptop and it'll be running. And there's other things that people respect and use and that are interesting, but you have to work very hard to get them even running. You get your head.
I had always the feeling that actually the kind of data dependencies that you have in a theorem proving environment is significantly higher than you have in usual programming languages and so on. So that building an IDE with refactoring facilities would be much, much more complicated and also much more specific to one particular prover. Do you think that these technical challenges, which so far hampered us to build EPs, could be overcome somehow?
So you're right that the data dependencies are are tighter, stronger than they are, for instance, in Java. But I think that might be as likely to aid refactoring as to make it more difficult. There's the Java refactoring, which tries to take legacy code and actually generify it. And I think they've been driven to some sort of more AI-style techniques to try to find the right type parameters. But I think that probably in an automated theorem prover that you wouldn't have to fall back on these AI sort of guessing, exploring techniques as much. I mean, I think the other part of your question, which is that these things are really different, right, is really true. The one theorem prover is very different from another. And a refactoring that makes sense in Coke is going to be a pretty goofy idea in Isabelle, right? So I agree that the refactoring technology would not be reusable across theorem provers. That's true. I hope I've answered your question.
Yeah, in fact, you've answered mine too.
Okay. Go ahead.
So building your own IDE is kind of passé these days, but extending existing IDEs is pretty popular. Like, do you have ideas about where you might, what kind of substrates you might build these kinds of proof IDEs on top of?
Right. So at this point, everybody is saying Eclipse, Eclipse, right? And so there was a presentation again at UITP of a sort of lightweight skin in Eclipse for ACL2, which is another well-established theorem prover. And so I think that just the way things are tending, Eclipse is the way everybody will naturally go. There is some work. So to give you a little background, there has been a notion previously of putting a generic skin over a lot of different theorem provers, and this is called the Proof General project. And it was previously done in Emacs. So there's some Emacs something, and there's been this idea now to take the same concepts and to put them in Eclipse. And I cannot say that it has advanced very far itself. I think I remember the first time I downloaded the plugin, it just crashed Eclipse. So, and I just, that when those kinds of things happen, you're not really motivated to continue, just to find out if maybe it'll work for you. So I haven't gone much further. But it seems like the work on ACL2 has proceeded fairly well in Eclipse. The problem from my point of view is that, again, it's all about the interaction and not so much about the management. Go ahead.
Can a bit comment on the failure of the Eclipse, Proof General Eclipse project?
Mm-hmm.
Actually, one of the big problems there was that the IDE Eclipse is built around the idea of having continuous build and to have also very deep reflection on the programming language you're working with.
Mm-hmm.
And building plugins that have not this kind of facility. It is very hard, and moreover, it will turn out to be very hard to find a decent way to support mathematical symbol editing in Eclipse. So these were the major major reason that actually didn't work out.
Okay, yeah. I think one comment on that is that I think I see again at UITP that there's this notion that people are interested in representing these mathematical symbols. And of course, we do like them because they're succinct and expressive, and that's great. But at the same time, I think people who are coming more from the programming languages community are reasonably well satisfied with keywords and so forth. And well, you're not, I can see that. I'm satisfied with for, F-O-R-A-L-L, all, as opposed to the inverted A. But
Doesn't help the eye if you have very large proof states. Compact
oh,
notation
no,
helps.
I quite agree with you there. It does not. I agree with that. Go ahead.
So are the tools that you're talking about, do those work mostly on the proof scripts or on proof objects, like you do refactoring?
Right. So I actually am more interested in manipulating proof objects. That's one of my actual research goals, as opposed to what I was talking about here, which is more about tools that would help me advance my research goals. But I think there's a spectrum, really, of how ambitious the refactoring could be. And I think that the less ambitious refactorings would tend to try to manipulate proof scripts. Yeah. Go ahead.
So another question would be, how often have you seen or hear of proofs being worked on by multiple people? And if so, what kinds of IDE support would you advocate for supporting collaborative work? Not necessarily simultaneous, but collaborative work on proofs.
Okay, so there are a couple sorts of collaborative work on proofs. Yesterday I was at a workshop and people were talking about a rather large project to formalize a microkernel in Isabelle. And we have yet to see how collaborative working on proofs goes because their effort so far has just been in the formalization. They haven't actually worked toward developing the proof except what is necessary to develop the formalization. They had to demonstrate termination in order to get Isabelle in this case to accept it. So in that sense, we have yet to see how collaborative proof development works. Other things are somewhat more anecdotal. There were a couple papers written about development of the four-color theorem in Coq, which took a number of years and a few people. And the anecdotal evidence was that I think they sort of ran on separate tracks for a bit, and then they spent several months refactoring to get the different parts to fit together again. So that kind of sort of incompatibility problem is real, and it took real skillful people several months to bring the two parts together. It might have been better if they'd had the ability to work together, to be in sync. That might have helped, but I don't know how they would have done that. Then stepping back a bit and talking about not people just collaborating on a project, but the fact that there are lemmas out there, there are libraries that people can use. And this is a different sort of more distant collaboration, like somebody writes a library and then you hope to use it, right? It's not the same thing. In terms of that, even that is rather difficult because you have to guess wildly what they might have called their particular lemma, right? So even that kind of thing is a challenge. I've thought of two things. One, it would be nice if other people rated their favorite libraries, because I've found myself in the situation where I actually used lemmas from one library only to find that there was a much better library out there which allowed me to be more succinct and more central. So it would be nice if there was sort of a Google rating of libraries. We've all used this one, and that one could win. And then otherwise, I was actually talking to a guy who is very much involved in something called the Mowgli and Helm projects. And these are projects which try to actually keep databases of libraries of lemmas and theorems online and make them searchable. And when I was talking to him, I've seen it, and it's always seemed to be sort of broken or inaccessible whenever I've been there. But when I was talking to him and he was actually spelling out how you can search for the lemma you're looking for, it made it sound like a useful practical tool for me. And so I was going to go back and check, and if it didn't work, I was going to write him an email and tell him how much I wanted it to work and so forth. So I hope I've answered your question more or less. Yeah.
Well, thanks very much again.